All right, hey everybody, it's your boy Dr. Naz again, and we're going to be talking about circle mensuration in exercise 15E. So just a few definitions before we start out of circle geometry. So if I draw a circle here, I'm just going to talk about what some of these words mean, okay? So you probably have already come across most of them, but I just got to formalize it for you. So a chord is a line segment with endpoint on the circle. So the red one, for example, that's your chord, okay? Now, an arc is the leftover circumference of the circle when you cut the circle with a chord. Okay, so if you have a look, I've now, with this chord, split the circle into two parts. So I've split it into this part in blue, okay? And then I split it into this part in pink. There's a big part and there's a small part. Right, and then just to be more precise, the blue part is what we call the minor arc. So it's the shorter of the two. And then the pink part is what we call the major arc, okay? So the next one is a segment. It's the two interior regions of a circle when divided by a chord, okay? So you have a segment here. So this is one segment in blue, okay? And then another segment over here in yellow, okay? This big thing over here. That's all one segment as well, all right? So you get two segments when you divide your circle by a chord. All right, so it's the yellow is half the segment. So it's one of the segments, sorry, and then the blue is the smaller segment, okay? Now the other one is a sector, which is a portion of a circle divided by two radii coming from the center of the circle to any point on the circumference. So just to kind of line up everything we've done already, I'm going to draw my two radii. So remember the center of the circle, you got the center here, okay? I'm going to draw my two radii to touch these two red points. Okay, so that's a radii. And then this entire region here, this green region here, okay, that's what we call a sector. So hopefully that makes sense. And we're going to figure out how to calculate some of these things. So the first one we're going to talk about is arc length of a circle. Okay, so hopefully this one's pretty self-explanatory. So the arc length is going to be, if you think about the circumference of a circle, it's 2 pi r, because an arc length is only considering a theta amount of the circle from a total of 360 possible degrees. So what I'm saying for our example here, this is our arc length, yeah? This angle over here formed by theta, that's the only portion of the circle that we're considering out of the total 360 degrees. So you get your normal formula for the circumference of a circle and then you multiply it by theta on 360 degrees, okay? Theta is the angle made by the chord to the center, okay? And then you put it all together, you end up getting pi r theta on 180 degrees. And then if you're working in radians, then your arc length is just going to be equal to r times theta, okay? For your chord length, let's have a think about the chord length, all right? So if I draw a circle, so we're interested in this length over here, okay? So that's a chord of a circle. You know the center of the circle's here. So if I just draw this over here and over here, yeah, that's a radii, and then you have some angle here, theta, which forms a circle. All right, if I kind of zoom in a little bit, I'm going to split the circle down the middle. Okay, so we know that each of these angles now are theta on 2 and theta on 2, okay? So we know since we split the chord down the middle, we know that this length is going to be the same as this length, okay? And we just need to find one of these lengths. So we know, just having a look at this circle really quickly, that sine of theta on 2 is equal to opposite, which is x, over hypotenuse, which is r, which gives you that x, which is your interested quantity, is r sine theta on 2, okay? But because it's two of them to form the length of the chord, it's 2r sine theta on 2, which is what our formula says, okay? So hopefully that's quite simple. So just to kind of align with what the formula is saying, I'm going to label this side A and this side B, okay? All right, next up, we got the area of a sector. So the area of a sector has a pretty similar argument to the arc length, okay? So if you think about a sector of a circle, all right, just drawing the circle. So the sector forms some angle theta of the circle. Now, you know the whole area of a circle is pi r squared. But because we're only considering the theta portion out of the full rotation, which is 360 degrees, then for degrees, our angle formula is, pi r squared theta over 360, okay? And now to convert it to a radians formula, all we're going to do is set theta equals 180 over pi times theta, okay? That's the conversion between degrees and radians, and we just get a half r squared theta. All right, now the last one is the area of a segment. So if you have a look, they've kind of got what's a combination of a couple of things happening here. So the area of a segment comes from the fact that if I draw a circle, okay, and then I draw a chord, right, A to B, and then I draw center point, which is here, C, and then I draw the two radii from the center point to both the points A and B, okay? So we are interested in the area of the green. We're interested in the green area, yeah? We're interested in the area of a segment, okay? What we can do is we can calculate the area of a sector, okay? And we can subtract the area of the triangle that's formed by it. So the area of a sector, remember, so I'll highlight what I'm talking about. So in blue, okay? In fact, you know what? I'll just do it like that. And I'll say the area of green and blue is just the area of a sector, right? So that's just pi r squared theta on 360. We just talked about that before. So this angle over here is theta. Now the area of the blue, but on its own, you just got a triangle, right? So it's a half base times height, right? But what we learned is we can write height as c sine theta, okay? So we end up getting a half BC sine of theta. A half BC sine theta. So B and C, remember, are the two sides that create theta. So they're both length r. So you end up getting a half r squared sine theta, okay? So we're just interested in the area of green. So we have to subtract that result from the previous result, which is the area of green plus blue. So we end up with just the area of green is equal to pi r squared theta on 360 multiplied by 1/2 r squared sine of theta. Sorry, a little bit tight. And then that's our result if we have a look at our result in degrees. And then in radians, the formula hasn't really worked properly. There should be a minus 1/2 r squared sine of theta there as well. Let's have a look at question 1. Shade the area and calculate the following quantities for the circle below. So the length of the minor arc. So part A, we're going to do in blue, the length of the minor arc. So remember, that's the minor arc because it's the shorter of the two. And its length is equal to, well, it's normally 2 pi r for the whole circle, but because it's a minor arc, it's theta on 360. Now, if you think about it, theta is 120. 120 divided by 360 is just 1/3. So you end up getting 2/3 pi r. But because we know this length over here is 6 centimeters, well, it's just 2/3 times 6 pi. Okay, which gives you, what did it give you? 4 pi. All right, and you can just leave it like that and then just chuck a little centimeters at the end. All right, part B, the length of the major arc. So the major arc is the larger of the two options. Okay, so the length of that one is just going to be 2 pi r minus, sorry, not minus. I guess you can do it with minus as well if you really wanted to. But there's a couple of ways you can do that. So theta in this case, so if it's 120 for the inside, for the smaller of the two, then it's 240 for the larger, because they have to sum to 360. Okay, so you end up getting 2/3, because 240 divided by 360 is 2/3, times, now 2 pi r, but r is 6, you get 12 pi. Okay, and that simplifies to 8 pi centimeters. Okay, and you can confirm that that works because you know that the total circumference is 2 pi r, which is 12 pi centimeters. And if you have a look, 4 pi plus 8 pi is 12 pi, yeah? Add these two together, they should give the total circumference. So that's a good thing. All right, part C is the length of the chord. So let's highlight the chord and do the problem. All right, so I'll do it in this beige color. That's the chord, remember? All right. So what's the length of the chord? We can just apply our formula, but we could also figure it out by breaking it down into a triangle if you don't remember the formula. So if you go back to the length of a chord, it's 2r sine theta on 2. So length equals 2r sine theta on 2. So in this case, r is 6 centimeters and theta on 2 is 60. So you end up with 12 sine of 60 degrees. Okay, now if you remember your exact values, sine of 60 degrees is root 3 on 2. So you end up with 12 times root 3 on 2, which is just 6 root 3 centimeters. Okay. Now part D is the area of the sector. I'm going to do this in green. So the sector, I probably should have been a little bit more specific here and talked about which sector, but it's this thing over here. That's what I'm talking about, okay? So this whole region here. That's the sector, okay? So let's talk about the area of that thing. So the area is, remember, pi r squared is the area of the whole circle, but because you're only taking 120 degrees of the 360 degrees, then you multiply it by theta on 360. Okay? Remember, r is 6, so we end up with 36 pi, since 6 squared is 36, times 2/3. Sorry, 1/3, because 120 over 360 is 1/3. Okay, 36 divided by 3 is 12, so you end up with just 12 pi centimeters squared, because it's an area. All right, now part E is the area of the segment, so I'll do the segment in whatever color we have left, pink, all right? So the segment, remember, is just this portion of it. All right, that's the segment. I'll just try and shade it the best I can. All right, so the area of the segment, remember, is the area of the sector minus the area of the triangle, which is a half r squared sine of theta. Okay, using the area of the triangle formula. So you end up getting, remember, theta on 360 is just 2/3. Well, actually, we know that quantity from part D, so I'm just going to put in 12 pi straight away for the first part, minus. Now we got a half r squared sine of theta. So a half times r squared, which is 36, times sine of 120 degrees. Ooh. 120 degrees, okay, which simplifies to 12 pi minus 18. Now, sine of 120 degrees is in the second quadrant, so it's positive, and its basic angle would be pi minus theta, so it's 180 minus 120, which is 60 degrees. So we end up with sine of 60 degrees, okay, which is 12 pi minus, we know sine of 60 degrees is root 3 on 2. So we end up with 9 root 3 centimeters squared, because it's an area, okay? Does that make sense? All right, let's have a look at question 2. So in the figure below, O is the center of the circle, and AB equals 12 centimeters and AC equals 13 centimeters. Find the area of the segment formed by the chord BC. So the chord BC is here. The segment formed by that chord would be the area of this thing. So let me just shade straight away what we're interested in. I'll do it in yellow. Okay, we're interested in the area of this thing. All right. Now, let's have a look at the information that we're given. So we're given that AB is 12 centimeters, AC is 13 centimeters. So let's label a couple of things here. So AB is 12 centimeters, AC is 13 centimeters. Now, the good news is there's actually a way that we can tell that this triangle that's kind of inscribed in the circle is a right angled triangle, okay? So the idea, well, there's actually a theorem that tells you that any line that passes through the center, okay, it could be this line over here, So any essentially diameter of the circle, which I haven't drawn very well because my pen's not allowing me to, but let me just fix it. Any diameter of a circle that creates a triangle. So this point can go anywhere on the circle we're talking on. Let's just even put it here. Is created such that that angle there is always a right angle triangle. Okay? So what does that mean? Can you see that we've got two radii here? So we've got a diameter, and then we've got a triangle that's inscribed inside the circle, which means that that angle has to be 90 degrees, okay? So if that angle is 90 degrees and we've got a 13 centimeter side and a 12 centimeter side, then actually it tells us something really nice about this side over here, which is the fact that it is a Pythagorean triple, yeah? It's a really famous one, 5, 12, 13, okay? So this side over here is 5 centimeters. And we also know that this side over here, it's just the radius of the circle, so it's 6.5 centimeters. And this side over here is also 6.5 centimeters, okay? So we want to find the area of the segment, right? So the area is just going to be equal to the area of the sector, which is pi r squared theta on 360, minus the area of the triangle that is left over, okay? So that's going to be a half r squared sine of theta, all right? So let's have a look at, well, we need to find theta, which is the angle that is formed by the sector, okay? So this angle over here we need to find. We can do that using the cosine rule, right? Because we can form our little, what I like to call our little arrow. Okay, so the two tops of the tip of the arrow, the two parts of it goes through the 6.5. The tail, even though I haven't drawn it very well, that goes through the 5. And then the head of it is the theta. So we know that cos of, actually, you know what? I'll just write in the formula straight away. So in this case, what I'm going to label as A, sorry, again, this, I might rename this area. All right, so what I'm going to call A is the angle theta, okay? That's equal to, well, we know the formula from before, right? It's B squared plus C squared minus A squared divided by 2BC, and I forgot an important component, which is the fact that you take the inverse cos of this thing. Okay, so we get inverse cos of this thing, all right? So remember, the only thing that's essential here is that our A is 5 centimeters. So we end up with inverse cos of 6.5 squared plus 6.5 squared minus 5 squared divided by 2 times 6.5 squared, okay? And now, put that into your calculator. Now, you guys may have noticed there's actually like a few ways you can do this. You don't have to do the cosine rule, but I guess just because we're practicing it, we are. You could also, for example, just split this triangle down the middle. You know that this length over here would be 2.5, this length 6.5. You can find the height directly just by using Pythag, and then you can just use a half base times height instead of this formula. So you can use whichever way is best for you. I'm just using this way because we're practicing these rules. So if I go inverse cos of, just putting it into my calculator, guys, give me 1 second for this. We end up with 45.24 roughly. Okay, so 45.24 degrees. That's the angle A. Now we want to find the area of the whole thing. So the area is equal to pi r squared, which is 6.5 squared, theta, which is 45.24 over 360 minus 1/2 r squared, so 6.5 squared, times sine of theta, which is 45.24. This is definitely, just to throw it in your calculator question, we get an answer of 1.68, rounds to 1.68. Okay, and because it's in centimeters, we do centimeters squared. All right, so hopefully that exercise makes sense, and you guys just need to go ahead and finish those problems in your workbook, which I'll be checking at the beginning of term 4. Thanks, guys.